Good morning, everybody. We are going to start Module 5, Lecture 2. We're going to be looking at our vision sensors. Like I mentioned in the last lecture and previous videos, cameras need their own entire lecture by themselves because there's just a lot of information about them. So we're going to be understanding how we're using cameras in the industry. This is our agenda for today, so this is the plan. This video is broken up into two sections again. So the goal is you're going to be understanding how machine vision systems work, how we use LiDARs with the combination of these vision sensors, and looking at these modern vision tools, and understanding how we are using them in robotic systems. So these are the goals for you guys today. I want you to understand the role of machine vision systems, understand how we use modern vision libraries, and then connecting everything all together. So, when we look at a robot, why do robots need to see? Well, exactly like humans, humans, we rely on 80% of our vision to process information. This same idea applies to robots. A robot without vision is limited to touch or proximity. It can't really see where an object's, what it's looking at, or detect the changes in its surroundings. So that's when machine vision systems come in. This gives the robots the ability to perform critical functions. So we have inspection, detecting flaws or missing components and parts. We have guidance, it's just helping the robot identify the location, the orientation of parts, and precise movements. And then safety, detecting if humans or objects enters its work zones and needs to know if it needs to shut down. So this concept is very, very similar to our own sensory system. We have our eyes, our brain, and our hands. So in robotics, our eyes become the camera. Our brain is the microcontroller, or the controller, and our hand is the end effector, like our gripper or suction cup, whatever we're using. So looking at a camera, cameras are the robot's eyes. They transform light into usable data because, again, our microcontroller can only understand zeros and ones. It has to understand numerical data. It can't just process an image just how we do. We just look at an image and we can tell what things are. This process begins with light entering through the lens. It focuses onto an image sensor, so either a CCD or a CMOS. We're going to talk about that in depth in a little bit later. And then it converts all of these into electrical signals that represent each single pixel. So each pixel corresponds to the brightness and a color of a tiny point in that image. There are a lot of key characteristics when we're looking at a camera. There's resolution, so that determines how sharp or detailed an image is, and it's measuring it by pixels. So the more pixels, the more detail that there are in that image. Frame rate, it's going to determine how many images per second the camera's capturing. So this is really important for moving parts. And then we have global versus rolling shutter. So global shutter is going to capture the entire frame at once, so there's zero room for motion blur. We use this for fast industrial processing, so like on a conveyor belt line. And then we have rolling shutter. So this captures line by line. Only issue can cause a lot of distortion in objects, especially objects that are moving. So I want you to think about this, like different types of cameras that we're using, the different things that we have to consider when we're picking a camera. So let's talk a little bit more kind of about rolling shutter and global shutter. Honestly, the most common one that's used is global shutter. This is what I've used multiple times before, especially when you have mobile robots. You are moving, the objects around you are moving. You need to just be able to capture an image all at once. Rolling shutter, it's going to cause too much blur because it's image line by line that's pretty much captured instead of one instance in that time. So when you look at that, we can see here Look at the rolling shutter. Look how larger and kind of strange looking the blades of the fan looks compared to a global shutter where it's in that instant. Everything looks a lot more normal. Nothing's all like distorted. You know, we can see here there's quite a big difference. So global shutter is usually the way to go, especially we're always handling moving parts. Only downside, you do need a little bit of a higher processing system. They're a little bit more expensive. Obviously, it's better. It's going to be more expensive. So I think it's pretty obvious there's more than just one type of camera. There's a whole bunch of different types of vision sensors that are used to capture the different types of information. When we look at 2D cameras, their output is a flat image, so it's just pixels. We use this for surface inspection, reading barcodes, and even just checking alignments. And then we have our 3D cameras. We use this for depth mapping, for also looking at images. We can measure distance and shapes now. We can see that it's not just like a flat circle. Maybe, okay, no, this is a cylinder now. And then we have LiDARs. LiDARs we use for creating 3D points in a cloud. Use them for distance mapping in scenarios where we just can't really see because we don't have the proper lighting. LiDARs, we're going to get into that. It relies on lasers. And we have our infrared cameras. So, thermal imaging, it can detect heat, coldness. And then we have our global shutter, which we just talked about a little bit, of just capturing an entire frame at once. And I do want to make it very clear is that you're not just picking one camera when you're using when you're making a robotic system. For example, when I was doing the cave exploring robots, we use a combination of infrared cameras and LiDAR cameras. And the reason being was like LiDAR cameras, they're 3D mapping. They're constantly taking in data and they instantly giving it back to the controller, and the controller is constantly making real life decisions at a high rate. We can map how far the cave walls, their depth, if the terrain ahead of us, if we have a drop. And the reason that we were using infrared cameras was in these caves you have sometimes you have actual like rivers and streams that are going through these caves. Sometimes you actually may have waterfalls that are inside of them. You need to be able to detect like water and just like hotspot areas. Cave water is cooler than the actual walls, just because it's a large puddle. There is actually water on all the cave walls, but when you're looking at a puddle, you can definitely tell based off the depth with the LiDAR. And then looking at the infrared camera, seeing that condensed area of water, not to drive through that because you're going to mess up your whole entire robot system by getting it damaged with water. So that's just one example. There's so many examples out there though, but you're always combining multiple cameras together to make up a system. So just like our cameras, like on our phone, or if you have like an actual handheld camera, there are a couple of things you need to consider in lighting and the optics of it. A camera is always going to need good lighting. If there is bad lighting, it's not going to know what it's looking at. So, poor lighting conditions can cause even the best camera in the world to just produce useless data. Think of a blurry or a shadowed image that you take with your phone. It's blurry, you can't really make out the detail. There's too much shadow, you can't make out any details. Robots are going to face the exact same problem. Lighting needs to be consistent, it needs to be even, and it needs to be bright enough, but not too bright, that it can reliably use the image as a form of vision. So there are a couple common techniques that we use to fix this. We have backlighting. So we're shining a light behind the object, so good for detecting shapes or edges. We have ring lighting. So it provides like an even amount of brightness illuminating the area. It's eliminating shadows. Pretty common in assembly and inspection lines. And then we have structured lighting. So that can project patterns like stripes or dots. We can use it for detecting surface defects or even depth. So kind of, again, think about when you're taking a photo, what are things that you have to consider? If the lighting's too bright or too dark, what happens? This is going to lead into your discussion post, and we'll talk more about this in class. But feel free to answer this on the discussion for extra credit. I'm asking you guys, what do you think that a robot has to consider? Do you think a robot has to consider those same factors of lighting and speed? What can cause distortion? What's going to give you a perfect image quality? Now, you have to break down the whole entire, when we take an image, we don't just take an image and immediately give it to the controller. Like we've been talking about. The controller only reads zeros and ones, only binary data. An image has to be translated over into that for a controller to understand even what it's looking at, so it can tell the robot what it needs to do. So every vision system begins with capturing the image. Again, the camera lens focuses light onto the image sensor, so either CCD or CMOS. So CCD, it's a charge-coupled device. It is converting light into electrical charge, and then it transfers it across the chip to read 1 pixel at a time. So it's reading one by one and making its data, telling it how bright it is, the color value that it is. So you can get that all translated over into the microcontroller. So they produce a high quality image with minimal amount of noise disturbance. And these work in low lighting because it's one by one, every single pixel is evaluated. It is a little bit slower though, again, because of this one by one system that it's doing. We typically are only seeing this on a higher end or like scientific cameras. You can see this in the Mars rover. Downside, again, unless you're JPL, you cannot afford these cameras at home. They're very expensive and they are power hungry systems. They require an insane amount of power to operate. So that's why, like I said, unless you are some aerospace company or you have a lot of money, you cannot be using these at home. It's almost impossible. And then we have CMOS, which stands for complementary metal oxide semiconductors. So with this, each pixel has its own amplifier, and it converts light to a voltage directly on site. So it enables a faster capture, and it takes less power to use these sensors. We see them on our smartphones, webcams, and of course, this is the most common one that's used in industrial robotics. Downside, again, we're not evaluating pixel by pixel, so our image can be a little bit more noisy, may not be as clear, be a little bit blurry. I would say, though, every 4 to 5 years, there is actually a major breakthrough that's making these CMOS chips actually pretty close to being similar to the CCD chips. But it's still going to take a while to get there. So the quick breakdown of it is just CCD, better image quality, it is slower, it does cost more. CMOS, it's faster, it's cheaper, it's just more efficient. It's getting back into the image capturing, so each tiny element, each pixel, converts light intensity into an electrical signal. So for example, we had a 640 by 480 camera. That is equivalent to 307,200 pixels. Each one has its own recording of brightness and sometimes even color. So it's a grade of thousands and thousands of tiny lights that are getting measured based off of their brightness. Now, stage 2 is digital representation. So once we've captured that image, the image is represented digitally by numbers. So in like a grayscale, 0 is going to be black, and then we go all the way up to 255, which is white. In color, each pixel is represented by 3 values. It's our RGB colors, red, green, blue. So an image is essentially, when it's getting translated over into a digital data, it's just one big matrix with a whole bunch of numbers. Instead of the actual image of pixel by pixel, each one is represented by a number that is then sent over to the controller that we can actually read. So robot's not actually seeing an image like we do, it's analyzing just numerical data. And that leads us over into stage 3. So like with everything, raw camera data, it's often noisy, it's unclear what we're looking at, it's just a raw photo. The robot needs to apply a image processing system to it to clean up this whole entire system. So that starts with three main parts. It's filtering, so we're enhancing the edges, removing any blurs. Thresholding, we're separating objects from backgrounds and based on the brightness. And we have edge detection, so we're trying to find outlines or shapes so we can understand into our next stage our features, understanding the features. So stage 4, after all this filtering is done, the system's looking for specific features that it can describe mathematically. So like corners, lines, circles, color blobs, or like textures. This is what's helping the robot recognize where an object begins or where it even ends. So for instance, it can identify a circle, and it's looking at the circle, and we're telling the system, hey, this whole entire time you're supposed to be looking for screw heads. The robot sees a circle on the image, it knows that that's a screw head, because typically a screw head is a circular top. And say we're looking at a box. The robot doesn't see a box, but it sees straight lines, so now it knows that it's looking at a box. So pretty much all of these features are giving clues to what the robot is looking at, if what it's looking at is actually the correct item. So that's very similar to how our brain works. We can look at an object, our brain detects the edges and patterns before we actually fully recognize an object, and then we put it together. Oh, that's so and so. Oh, that's a box. We have to look at the features first. And then that breaks into stage 5 and 6. And again, these work together. This whole entire system's happening in microseconds. So once a robot has extracted features, it starts to interpret them. So again, the example, circular object, it's a screw head. The line is off by 5 centimeters, by 5 degrees. We need to adjust the gripper by 5 degrees. The box appears empty. I can't take this. This is a defect. So finally, once all that's made, that the controller processes all that data and then tells the robot what it needs to do. It makes the robot decision. So if it's a defect, reject that part. If the position is offset, adjust the arm. If everything's all good, continue it down the line. It's this whole entire thing. It's a pipeline pretty much of we take our image, we give it a digital representation, so we're converting everything to numbers. We're reprocessing everything, so we're filtering everything, trying to just get some features out. We are then extracting those features and trying to understand them, and then interpreting them over for our robot then to make its decision. So this is a closed feedback loop. Again, so the camera isn't just seeing an image, it's actually helping the robot act based off of that image data. So moving on to LiDARs. LiDAR stands for light detection and ranging. It works by sending out laser pulses and measuring how long they take to bounce back. Very, very similar to an ultrasonic sensor. So each reflection point gives the system one piece of distance information by forming a 3D point cloud. So essentially, millions and millions of dots that outline the environment. So a LiDAR can see pretty much even in darkness or in the poorest lighting, because it doesn't rely on visible lighting. It doesn't need an actual light to tell what it's looking at. It only is relying on these lasers. So you actually end up combining LiDARs with a different camera, usually a 3D camera. So the camera's going to capture your visual details, so color, texture, or labels. A LiDAR camera is going to capture your 3D structure, so distance, shape, depth, together. Now the robot has a full understanding of what it's looking at and where it's looking at it in space. It has a full understanding of its world now. So where do we use these? We use them in navigation or obstacle avoidance, SLAM, simultaneous localization and mapping. Pretty much that is the robot is in an unknown area and it's trying to locate itself within that area. And this is actually what we use in our cave exploring robot. It is a really complicated system. We can talk about it more for sure. It honestly is a lecture of its own on how to use it. I don't even think we have strong enough of a resources to use it. It does require a lot of power to use. Again, you're mapping a system. The robot knows where it enters. It doesn't know where the end is, though, and it's trying to figure out, have I reached the end? How big of an area am I exploring? Now I'm getting sidetracked. Like I said, we can talk about this for a while, and so if you have any questions, please feel free to ask. And then we have the automated guided vehicles. So this is, guiding, the robots are guiding itself in the warehouse. And then we have drones, surveying and surveying, the area, the terrain, and, trying to map that area. So LiDAR is most commonly it's used either with a 2D or 3D camera. They're great on their own, but they definitely, to get more enhanced details at everything, using it with another camera system makes your robot really prone to not having any issues. So this slide is just breaking down how vision and LiDAR data pretty much all comes together. First, we have our camera is going to capture the image. So we're producing a 2D color frame that has textures and labels. Our LiDAR is going to start scanning. We're generating our 3D point cloud on an XYZ coordinate. And then we have systems that will calibrate and align these. So we're taking the image and overlaying it over the 3D LiDAR model. So we're overlaying a photo over a wireframe pretty much. And then the next step, which is the most important, is sensor fusion. So each LiDAR point is matched with a color label from the camera image. That results in a very detailed 3D colored map. So again, the robot knows exactly what it's looking at, how far it is, the shape of it. It knows everything about its current image. And then again, final thing, robot decision. The robot decides what it does with that information. If it needs to go more left, more right, how many degrees it needs to move, how far it can go. So pretty much the whole entire end goal of this is we're getting context and adding precision to it. The robot doesn't just know that something is here. It knows what it is and where it is exactly and where it's sitting in space.